Moving on. All right. I think we're going to end with associativity and we're going to call it a day. So last characteristic of caches. We have so far dealt with fully associative caches. What that means is that any memory location can be copied to any cache line. So back here, any of these cache lines could have any memory reference over there. And it ends up being that, we check every cache tag to determine whether the cache is in the line. This ends up being a problem when you have many cache lines because you have to check a lot of cache tags in parallel. So what we can do is basically bank it or make them sets of cache lines. So then we can only basically search the set or the bank of cache lines as opposed to the entire cache, and that's what associativity deals with. But before we go into that, let's go with the exact opposite of what fully associative is, so you can get an idea of what's happening, and it's called direct map. If we redesign the cache to eliminate the requirement for parallel lookups, namely, every piece of memory can only go into one certain cache line. They partition memory into many regions. Each memory region has a single cache line in which data can be placed. You then only need to check a single tag, the one associated with it, which is a lot faster than a ton of parallel tags. Let's look at the picture.
Ooh, different colors. Pictures.
Whoa.
Whoa.
Why do you change colors?
It's a pattern.
There is a pattern. So, how many cache lines do we have? 4. Great.
0 to 3.
Good job. How many blocks are stored in each cache line? 2. All right. So let's think about this. Now we're going to say that these 2 blocks will either store these 2 or those 2 and nothing else. The blue will store these 2 and those 2, nothing else. The purple can either store those 2 or those 2, nothing else. And is that indigo, magenta, violet, purple? Purple can store those 2 and nothing else. How do we enforce this?
I feel like there's going to be a problem.
Like an
with
indigo.
this.
Oh yeah, there is.
Because what if you need to keep the one, but you want to access the other one as well?
Very astute, yes. That's exactly what's going to happen.
Sadness will occur.
Kind of, yeah, but look what happened to our tags. The block offset's 1. The set index actually tells you which bank to look into, and your tag ends up being 1 whole bit.
Yeah.
Isn't that a lot easier to check?
Yeah.
Yeah.
You sound so sad.
Now let's go watch an example here.
Ooh, different colors.
L or U, by the way, is now useless because you always evict one line, right? It's directed. You can only read into one thing, so you can only evict one line. We're going to simplify this and make it so you only have 2 cache lines, and we'll go ahead and start this example. Read from 1. Miss. Why does it go into that line? Well, the address is 0001. That's the block offset. I love the squeakiness. This is the set bit. We only have 2 sets, so we either choose the top set 0 or the bottom set 1. And then you have those 2 bits to begin with, which are the tag itself. Now, see how that got calculated?
Yes.
All right. I'm going to erase it. We read from 5. Where does 5 go?
It goes in that top one. Right?
Yeah, so who gets evicted?
First one.
First one. That's a miss. He gets evicted. Because we can't read to the second one because we've set up our tag or cache to be direct map. Okay? Now we're going to store into 2. What happens?
It's a miss, but it gets stored in the bottom one.
Yeah, so we'll assume right allocate, right back cache. So we got a dirty bit, stores at the bottom. Yeah. Read from 7. What is that?
That's a miss. you gotta store the stuff in the cache back into the memory.
Right. Who's going to get evicted?
The second one.
Yep. Second one gets evicted. How about the 4?
That is a hit.
Is that a hit?
Yeah.
Finally we get a hit. Okay.
Finally, one hit.
Alright, so this is a little weird at first, but this ends up being very important. Y'all see what's happening here?
Yeah.
Yeah, we're basically banking the cash. Alright. Okay. Here we go. This is where things are going to start getting mathematically challenging.
I don't like that.
Always going to be great. Show the breakdown of the address for the following configuration. 32 bits. I'm helping you out here, guys. The whole thing must be 32 bits. Okay? All right, your cache is 16 kilobytes. All right? It's direct mapped, meaning that the set in every byte in main memory only maps to one cache line. And you have a 32 byte blocks. All right. What is the distribution of bits here? When you do this, start with your block offset because that's the easiest. If you have a 32 byte blocks, what must your offset be?
5 bits.
5 bits, great. Okay, now things start getting a little complicated. So your block offset's 5, you have 32 bytes per block offset, and you have a 16K cache. How many cache lines are there going to be?
500.
Wait, what?
500?
You're close.
Well, something.
What's 16K? Write it in as a power of 2.
Yeah, okay.
And then,
16 is to the 4th.
16 is.
That's 2 to the 4th, but 16K, so it's 2 to the 14th.
14. Oh. JK.
Right. Y'all see that?
Mm-hmm.
Okay.
You're saying 16,000?
Yeah, 16,000.
Yeah.
What was it? 16,386. Yeah.
No.
Okay. So that's how many bytes you have in your cache. Each block is going to have 32 bytes, so you're going to divide it by 2 to the 5th, which equals,
2 to the 9.
that's how many cache lines you have. Because each cache line is going to have 32 bytes in it, and you have 16K bytes in total, so each cache line, you're going to have 2 to the 9th caches, aka 512. You were close. I said close, but 512. All right. So you have 512 cache lines. How many, and it's direct map. If it's direct mapped, once you have this number, how many bits are going to be part of the set?
1. So yes or no?
512.
No.
Close, but how many bits does it take to represent 0 to 511?
No,
No,
9.
No.
Oh yeah, I was right.
And the rest are in your tag.
And the rest are in your tag, which means that this is what?
Explain why.
It's 2 to the 9. You've got the 2 to the 9 right there.
Okay.
Yes, but no.
So it's 9.
So when you have your address, these 9 bits tell you which cache line to go to. These 5 bits are the offset on that cache line, and then your tag is another 18 bits to whether it's in that cache line or not. In other words, let me say that in a different order. When you go to see if your address is in the cache, you jump to the set by what these set bits are. You see if that tag matches your tag. If it doesn't, it's a miss. If it does, then you just need to jump to the block offset over here to find the byte and read it in. Any questions on this?
Let's do the 2.
So, sorry.
Mhm.
The block offset, like, so how we originally were using 4 bits and 3 were the tag, and then there was 1 as block offset.
Right.
And it was either 0 or 1.
Right, because you only had 2 blocks.
Right.
Or
So
2
now
bytes in your
we
block,
have
sorry.
9 lines.
You have 2 to the 9 cache lines, so 512 cache lines. Each cache line has 32 bytes in it,
Okay.
and it's
So
blocked.
we need 5
5
Bits
bits
to
of the
represent.
address represent where to go in that block.
Within each set.
Which 5 bits within each cache line, and it happens that each set is a cache line right now. Right now, every set in a cache line are the same. That's about ready to change.
Awesome. So disregard everything.
Because you can think of this as direct map is one set. There is only one item per your set, and it is that cache line. So that's about ready to change. All right, any questions on this? It's about ready to get a little more confusing.
I was hoping you'd get less.
Oh, class
Oh.
problems. Sweet.
Oh
Yeah. I love class problems. Who's next?
Not map, it's all gray.
no. Why is it all gray?
Why is that four?
Why not?
Gray's
What are you against gray? It has feelings too, you know.
Yeah, they're gray feelings.
Assume this is direct map. I got rid of the colors, so you would have to actually think about it. Who's ready to do this one?
Sure. I'll do it.
Did you get rid of the colors, or is that just how the slides
I
happen?
know, it's like, I was like,
Yes.
Yes.
So let's see. Just to make this easier for me, I'm gonna do like block them off like this.
Yeah.
Great. And so that
And
way
it's
these
gray.
two go there and these two go there. Okay, so let's see. I'll load 3 into register 1, and that's a miss, so alright, so 3. So that's gonna go here, and so dirty bit 0 because we're not writing anything. Tag is gonna be 0, 0, and so you just write everything in here. And then
The
so that
second
goes into
one?
register 1.
The third one's 120.
Oh, thank you. I just blew right through that. Super. So register 2 is 12. I mean, that's a miss, so that's gonna get loaded into here. So got 19.
What's the tag?
The tag is, well, let's see, because that would be
Write
12
write 12
is-
out in binary, which is 1
Yeah.
1 0 0.
yeah, 1 1 0 0.
The last bit is your offset. The
Yeah,
bit
this
before
is-
that's your set. So the
I-
previous 2 are your tag.
Yeah. So just 1 1 there, like that. Okay, great.
Finish
Then-
writing it. It's not dirty.
Dirty bits 0. So 19, 200, 210, 225, and we're loading it into register 2. So 19, great. Another miss. Just gonna go ahead and put that there for later, just in case. Alright, so you're gonna store whatever is in register 2 into 15. Oh, look at that. That's a hit. That's nice. So just register 2 is 19, so put 19 there. Change the dirty bit. 1. Let's see.
Doing great.
Thanks.
It's right
Alright,
back, so you don't write it. You don't do anything more. Go to the
Right.
next one.
Yeah, but we're about to because this is a miss.
Who gets
And
evicted?
this one gets evicted because it's in this block here, and this block goes there.
Right.
So we're gonna erase all this,
Whoa, whoa, whoa.
but first we're gonna write this into here.
Correct.
So 15, the value in 15 is gonna be 19 and not 225. So erase through that, and then we can go ahead and just I'm gonna use this eraser for what it's supposed to be used for. So I'm gonna load all of this in except 123 is gonna go right here, and tag is gonna be 0 1. Yeah. Yes. Okay. And dirty bit is 1 because we changed what's in 4, and so 150, 162, 173. Cool. And okay, great. I already put that as a miss. And we're gonna load into register 2 what's in, or load into register 2 what's in 9, and that is a miss. So I'm gonna erase all this, and then it's not a dirty bit. Tag is 1 0, and then where am I? Oh god, okay. 18, 21, 33, 28, and then registered 9. It's gonna, or memory address 9, that's gonna go to register 2. So 21. That's it, right?
Yep.
Cool.
Yeah. Wow, you get an actual applaud.
Oh yeah.
Congratulations.
Um,
All right, well, he
Oh,
erased
thanks.
it, but, you know, oh well.
Oh, was I
Everyone
not
was able to
supposed to?
follow,
Yeah.
except for the poor people online.
Alright.
Oh,
All right, so now we're going to make it even more complicated.
um,
Because with fully associative, you have a higher hit rate because you're able to basically use any cache line. But the problem is your tag lookups end up being incredibly slow because you have to do a lot of lookups in parallel, a lot of different tag lookups. Direct map, your tag lookups are great, but you end up having many more misses because you can only map each piece of memory to one line. So why don't we split the difference and maybe bank a couple of lines, or four lines, maybe 8 lines together that can map to a single piece of memory. So you're splitting the difference. Let's do something in between. Partition the memory into regions like direct map, but fewer partitions. Associate a region to a set of cache lines, and then check all the tags. Treat each line in a set like a fully associative cache. LRU policy is generally used here. All right, I think the example is really going to help.
Evictions.
Back to eviction. So notice that beforehand we had 4 sets, but now we're going to only have 2 sets where each set has 2 cache lines. What that does is instead of having a set index of 2 bits like we had in our direct maps, it shrinks it down to 1 bit because you're only choosing between 2 banks or 2 sets of memory. Your block offset's still 1, but now your tag is 2 bits. Okay. Everyone see what's going on? Yeah. If you use your book, it looks like this. Notice that these are both the same. Except for on this slide, it has the word 1 bits, and on the next one, it has 2 bits. But whatever. All right. But it fits better on these slides this way. So let's go ahead and run through this one. So read from 1, that is a miss. We validate, put the tag, not dirty, put the tag in. Notice you have the LRU for this set. Each set's going to have their own LRU, aka eviction notice. You read from 5.
The eviction
Yeah,
notice.
the eviction notice. He goes down there, changes the eviction notice to the top. Because with 5, you had, what was it, 0, 1, 0, 1. That set bit was still a 0. All right. Now you read from 7. Where's that one going to go? Yeah, the bottom one. Here we go. Now you see how there's 2 LRUs going on here. Read from 4. All right, that's actually you store into 4. So we changed those values. See what I did there?
Yep. It's dirty.
It's dirty now. Load from memory 0. Is that a hit or a miss? It's a hit. And this is advantageous because if it was direct map, this would have been a miss because that guy would have been evicted a while ago. But since we're using 2-way set associative, he's still in the cache. And then when you read from 8, is that a hit or a miss?
Yes.
It's going to be a miss. Who gets evicted?
Second part of the first one.
Yeah, second part of the first one. So he gets written back, and this guy gets loaded in. So you see how this is kind of doing a compromise between the two?
Yeah.
Yeah. All right. Here's the question: how do we determine how many set bits we should use?
Simulation.
There you go. Okay, here we go. Now to make it even harder.
Oh no. Oh no.
Oh yeah, here we go. Class props. Yeah. Yeah. So you got 32 bits. And you got the whole thing right here. You have the tag. You have the set. And you have the block offset. All right. 32-bit address. 16K cache. 4-way set associative. 64-byte blocks. All right. What do we do first?
Block offset.
Block.
Which is
6 by 6 bits.
6 bits. That's the easiest part.
Ye.
Yeah. Now the set. Oh boy. First off, how many cache lines do we have?
512 still, right?
Not this time. So how many? The size of the cache is 2 to the 14th divided by our block size, which is 2 to the
So
6th.
2 to the 8, which is
256 cache lines.
Ye.
Now, we have 256 cache lines. So if we were in a direct map, the set would be 8 bits. But we're not in direct map. We're using a 4-way set associative. So instead of using 8 bits here, we're going to use 2 to the 8th divided by 2 to the 2nd.
So
2 6. 6.
Right?
Yeah.
Yeah, okay.
okay.
6 bits. It's just easier to write your numbers like this, guys. Trust me.
That's how you get the bits.
All right. So if the block offset's 6 bits, the set is 6 bits. What's the tag?
20.
20 bits.
Now.
It's actually arithmetic, but that's okay. Any questions on this one? You will see this question.
Oh no 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 no.
Oh yeah.
No.
Oh yeah.
No, I can't.
Any other questions? All right, let's go to the next one. This one's actually a lot easier.
We need to get you a way to actually like write out the slides, or have another camera.
Nah. No, maybe. Nah. Nah.
Extra effort.
32-bit address, 16K cache, fully associative, 64-byte blocks. All right. What's the first thing we do?
Block offset. 6 bits.
All right. How many cache lines do we have?
8. Well, 2 to the 8.
2 to the 8, right. So 2 to the 14th minus 2 to the 6th. Well, I don't know why I wrote 8 there. 2 to the 8th. Fully associative. When you see fully associative, that means your set is how many bits? 0. You have no sets.
What?
Because any byte can go to any cache line. So it's fully associative, which makes the tag what?
The rest of it.
26. What was the tag on the previous one?
20.
20. Which one makes tag? Which one of these two is better for tag lookups?
The other one.
The previous one, right?
Like fully associative is basically what we were doing
At the
before,
very beginning.
At the very beginning.
Yep.
Okay.
Sadness.
Right.
Oh, look at all the
Yeah, class problem.
marker everywhere.
All right. I think this is the last one, actually. Who's next?
I guess I'll give it a go.
All right.
I don't want to, but
That's okay, Jonah. You just have the hardest one.
it's fine. Everything's fine.
It's just a two-way.
Can I go ahead?
associative
Can I
going
go
right
ahead
out
and
write
set-
that cache?
Can I go ahead and separate those by 2s?
If it helps.
Okay. So then I'm gonna go ahead.
So
and-
no.
Well, yeah.
You're writing with the marker weird.
Yeah, you are.
Or
See, Jonah.
You want me to
now
hold
you
it like
have
this?
feels.
You're using the bottom edge of the wedge.
So, here.
That's why it's not writing well. There you
Is
go.
that better?
Jonah,
Yeah.
we need to take you to marker school.
No.
Jonah, does that even help?
Yes,
The way
because
that you're
here.
bumping it, it doesn't look like it helps.
Why would you bump it?
Jonah, if you're gonna write those numbers, please make them 0, 1. Otherwise,
Where's the mark?
you're just gonna fail this class.
It's fine.
You're just gonna fail.
Everything's fine.
Can you not write it on the line either?
No, y'all are so mean. Here.
There you go.
0, 1, 0.
Only thing you learned from this class: zeros and ones.
All right.
Thank you.
So let's go ahead and teach the class.
Okay.
Number 11. We don't have that, so that's a miss. So we'll go ahead and add just a 1 there.
It's
Don't
a
worry about
10.
Real quick.
it. Not 10. It's a 1.
Cross out the 0.
All right.
Yeah.
There. For the people online.
That they can't even see.
All right.
So.
I know. All right. So this is gonna be 0 because we're not writing anything.
It's not dirty.
Well, hold on. Which cache line do we go to?
Oh.
We're gonna go to this one. Oh. Okay.
Yeah, which?
It's 1, so it's a second.
So we're gonna go to this one. So we're gonna go to the second one.
Right,
which is
the
down
second
here.
set. So we're going to the second set, and which one of the second sets do we use? First one, right? So Zach cache line, you got it.
Okay. So we'll go 0 here.
Doing great so far.
11 is 1, 1, 0, 1, 1.
Yep.
Yeah.
So the tag
So
is-
then this is just
1,
gonna
0,
be
1.
1, 0.
Yep.
1. Wait.
It's only 2,
Okay.
right?
It's
It's
2A.
like-
Yeah. So.
Yep.
Yeah. You got it.
And we don't care about the set, right?
The set. Well, no. The set tells you which set to use, and the block offset.
Oh,
tells you which
okay.
jump. So you have that right.
Oh.
Yeah.
So then this is 11, so we're gonna do 10, which is 33. And
Nice.
28. That's a nice 8.
All right,
that's
and then we're
nice.
gonna tell you register 1. Go 28. Right. All right. This 2, which is 2, which is in 1. So we go down here.
E.
Is it hit or miss?
It's a miss. So we'll update that. So 0.
We're not doing very well.
0, 0.
2, yeah. And then.
We're bad at Battleship.
That's a 3.
What?
I think that's an amazing 3, Jonah. Don't listen to him.
Hey.
There you go.
Is that better?
Yeah.
So much better.
All right.
So
never
why
read
wouldn't
that
that be in the top block?
Because the set. Hold on a second.
Because it's in the
Because they're in the
second
set of 1.
Yeah, they're in the set. The set bits for both of them is 1. So if we were to write out the address 11, see, real quick. The address of 11 or 11 in binary is 1, 0, 1, 1, and the address 2, aka in binary, is 0, 0, 1, 0. This is the set bit, which is saying you're in set 1, which is this bottom bank down here.
Okay.
Good
You
question.
can draw a line
Okay.
in between the two sets.
Jonah, is that a 1d3 in your R2?
What?
Is that
Ignore him.
1d3? No, R2. What's your?
Alright.
Well,
To
there
the
too.
left.
Oh, this?
Yeah.
To the left.
No.
Take it back.
Y'all know exactly what that is. All right, so
Do
then
we-
we're done with that. So then
do
we
we
go to
really-
this, which we're reading in 12, which we do
You're not
not.
reading, you-
Well, we're writing in.
Boring.
So that's not. So that's another miss.
Yes.
Then we go up here, and then we'll tag this as a
Is
30
it
bit because we have
30
to
bit?
write to 12. So.
No right allocate, so you don't evict. You just
Yeah,
write it
I
straight.
just
through.
write it in there. Which that's.
No.
No.
right allocate. Look up top. See the blue?
Oh, so then I just write it in 12.
Yes.
Oh,
You don't allocate anything in the cache.
I don't need that. Oh, that's easy.
Even though
We're
it's right
reading-
back, it's no right allocate. So when it's
123.
not in there, you just write it straight to memory.
Oh, okay.
123.
120. Thank you. All right.
That's the problem.
What?
I was just
Ignore
agreeing with
him.
this
Oh,
guy.
okay. All right. And then
With this guy over here.
so then 3, which 3 is a hit because we have that one, correct?
Yes. The second one.
Oh, we do have it. Okay.
Yeah.
Yeah, we
so you
do.
change it to a dirty bit.
Yeah. Okay.
All right, and it's
Dirty
right
bit.
back. So
Dirty
we
bit.
just-
Dirty bit.
Well, yeah. So we don't. I mean, so then I just change it there, right?
You just change it to cache.
Oh.
E. Dirty bit.
I think something got messed up because you were supposed to load 2, which is 120, and you wrote 123, which is 3.
Well, because you load in both 123. Wait.
Oh, I see what you're saying.
Oh,
I
there.
see what you're saying.
So
Yeah,
one-
Jonah.
120 should have been written to 12, and not 123.
Yeah, down there in memory.
Oh, okay. Easy fix.
Okay.
Jeez, Jonah.
Sorry. Alright. So then that's done, right?
Yep.
So then we
That's
go.
a hit, by the way.
Yes.
Yay, 1.
10.
So then, no, that zero's far away. There. Alright.
Colored
So
it.
then we load in from 7 to 3. We do not have 7. That's in 1. So then we
Nice.
evict.
Oh.
We evict this one.
Right.
Okay. Where's the
Hooray, sir.
Right, that's a
A
miss
9.
too. We'll go ahead and update miss. We evict this one, which is 0. 0, 1.
Wait, for 7?
Yeah.
Yes.
0, 1. So then we just go ahead and write that in, which is
162.
162, 173, 3.
There you go.
I knew you were gonna say something about it.
That
All right,
is questionable.
and then read that into.
Yeah, that was a little baby 7.
That poor little 2.
It's like a baby 7.
Nope, I'm gonna leave it alone. All right, and then number 10, which we do not have,
Correct.
so we have to evict this one. So then when we
Oh,
evict, well, when we evict this one, we have
Dirty
to
bit.
push 28
Yeah.
To 13.
to 13.
It's a dirty bit.
Will do. I'm just gonna come in.
It's okay, we're not recording it.
All right, and then we go ahead
Evict.
and get rid of that.
Miss, right?
Yeah, it's a miss.
Yeah. I'll just.
Oh, nice.
We are very bad at battleships.
Oh. Anyway, this is gonna be 0,
Because it was a dirty bit.
10, just 0, and then so we'll go ahead and write this in.
Yeah. It's
Um,
not 13.
Wait, where?
13 shouldn't have been changed to 28.
It wasn't 13.
It was 3.
It was
Who told me? Who told me 13?
I don't
Y'all
know.
are crazy.
Rest.
Y'all are crazy people.
No, you are.
Anyway, 10, and then we just read that one into register 2. So let me erase this. 33. And then that's it. Right?
E.
Yeah.
Yeah.
Done. Class is over.
Done.
All right.
We're
good job,
terrible,
Jonah.
and we're terrible at battleship. And I'm terrible at writing 3s and 2s.
Yep.
Any questions?
Who's writing? Stick to 7s. You can do 1s.
It's just a line.
Your
Just trying to
1s are
give you
nice.
something there.
Gee, thanks.
Yes.
So you can breathe good.
What?
I said his 7s are.
All right.